Hello, Honors Pre-Calculus. Today we're going to be learning lesson 7.6, the last lesson in Unit 7. The title is Probability. What we're going to be doing today is finding theoretical and experimental probability of events, probabilities of independent and dependent events, and finding probabilities of the complements of events. You'll know what all of those terms mean by the end of this lesson. The essential question is, how are the concepts of probability used to find the likelihood of different types of events? You should already know permutations and combinations, the concept of independent versus dependent, and the idea of sample space, which is also just like the total possibilities that could occur in a given event, which uses these concepts of permutations and combinations. Here's an example of something we'll be able to do. Manufacturer has determined that a machine averages one faulty unit for every 1,000 that it produces. What is the probability that an order of 200 units will have one or more faulty units? All right, so let's get started. All right, so here we go. Here are the notes for 7.6, probability. First, we're just going to read through the first couple of definitions and then try example 1. So an experiment is any happening for which the result is uncertain. An outcome is a possible result of an experiment. A sample space is the set of all possible outcomes of an experiment, and an event is any sub-collection of a sample space. So let's just start with those terms and take a look at example 1 at the bottom of the page. So we've got example 1, find the sample space for each of the following. One coin is tossed. So we're going to refer to the sample space with the capital letter S for, sample space. And when a coin is tossed, typically we consider one side to be heads and one side to be tails. So we're going to write that to be fancy in curly brackets with an H and a T. So that is the entire sample space. Those are all of the possibilities when you run an experiment of tossing one coin. If two coins are tossed, we're going to list each possible outcome with 2 letters. So it could be heads and then heads. It could be heads and then tails. It could be tails and then heads, or tails and tails. Those are all of the possibilities. All right, so we're going to do the same thing again for letter C, but with 3 coins. So we're going to have 3 letters. And so it could be heads, heads, heads. Heads, heads, tails. Could be heads, tails, heads, or heads, tails, tails. It could be tails, heads, heads, tails, heads, tails. Tails, tails, heads, or tails, tails, tails. Okay, is that all? 1, 2, 3, 4, 5, 6, 7, 8. Yep. And so you can hopefully see how I methodically did that. I started with kind of all heads. I changed the last H to a T, and then that's all the possibilities that start with 2 H's. So then I switched to HT, then I switched to TH, and then I switched to TT. And that's exactly the order that I went in letter B, but I just added an extra letter and switched it every time. So anyway, hopefully that makes sense. But that is example 1. So example 2 introduces us now to a probability within a sample space. So if we go back up to the top for a second, just so you can see, probability is if an event E has some n of E equally likely outcomes, and its sample space S has n of S equally likely outcomes, the probability of the event E is probability of E, n of E over n of S. So we're going to be making fractions here, right? It's division. Hopefully that makes sense. Let's apply it in letter A of example 2. 2 coins are tossed. What is the probability that both land heads up? So let's figure out the sample space and the events that we're interested in. So we're looking at 2 coins being tossed. We looked at that in example 1. So we know that the sample space is heads, 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 tails, tails, heads, or tails, tails, right? And so which of those are we interested in occurring in our specific question. What is the probability that both land heads up? Well, that only includes the HH, right? That's the only one where both land heads up. So that's the only one that we really want to include on the top of our fraction. So the probability of our event. And we don't usually write this fancy notation, but I'm going to write it just this once. So it's the number of occurrences of our event, which is 1, over the total number of occurrences in the sample space, which is 4. So we got 1/4. That's the probability. Probability can be listed as a fraction or a percent or a decimal. So any of these 3 answers are technically valid there. Let's look at letter B. Card is drawn from standard deck of playing cards. What is the probability that it is an ace? So this will be easiest if you know how decks of cards work. And just in case you don't, I'll talk you through it. There are 52 cards in a deck of cards, and there are 4 aces. So for drawing one card, 4 of the possibilities are ones that we're interested in or that give us a success. And there are 52 total possibilities in the sample space. So that reduces to 1/13. So that's what we're going to say is our final answer. Letter C, 2 6-sided dice are tossed. What is the probability that the total of the 2 dice is 7? So first of all, we have to figure out the sample space. So the total possibilities, and we're going to use some of our concepts from our previous lessons. It's 2 6-sided dice. So when we roll or toss the first die, there are 6 possibilities. And when we toss the second die, there are 6 more possibilities. So we multiply those to get 36 possible outcomes. And we want to know how many of those add up to 7. So let's set this up like we did previously as well. We'll say that here's the first die, and here's the second die. And let's say I roll a 1 on the first die. And what would I have to roll on the second die to get a 7? Well, it would be a 6, right? If I roll a 2, then I would have to roll a 5. 3 would be a 4. 4 would be a 3. 5 would be a 2, and a 6 would be a 1. And that's all of them. So how many different possibilities? What's that? 1, 2, 3, 4, 5, 6. So we have the probability of rolling a 7 is 6 out of 36, which is 1/6. There we go. Let's look at letter D. 12-sided dice can be constructed such that each of the numbers from 1 to 6 appear twice on each die. Prove that these dice can be used in any game requiring ordinary 6-sided dice without changing the probabilities of the various outcomes. So let's take a look. On a 6-sided die, the probability of rolling a 1 is 1 out of 6, right? There are 6 sides to the die, and one of them has a 1 on it. On a 12-sided die, that's described in this question, the probability of rolling a 1 would be what? It says that the numbers 1 to 6 appear twice on each die. So there's 2 1s, and there's 12 sides. So it still gives us 1/6. And that would be true for any number from 1 to 6. All of them have a probability of 1/6 on the 6-sided die and 1/6 on this style 12-sided die. So let's write a brief description of that. All numbers from 1 to 6 have a 1/6 probability of occurring on both dice. So there we go. All right, let's move on. Example 3, the probability of winning a lottery. In Arizona's The Pick game, a player chooses 6 different numbers from 1 to 44. If these 6 numbers match the 6 numbers drawn in any order by the lottery commission, the player wins or shares the top prize. What is the probability of winning the top prize if the player buys 1 ticket? Okay, so there's 6 numbers from 1 to 44. And so first we need to figure out the total possibilities. Well, how many possibilities? This is going to end up being a combination from our previous lessons. So if there are 44 possible numbers and we're interested in picking 6 of them, it's going to be 44C6. And that's because the order of the numbers doesn't matter, right? It says in any order. So we can pick 6 numbers and it doesn't matter what order we pick them in. If we pick the same numbers in a different order, it's the same set of numbers. So that's why it's a combination. Remember, in a combination order doesn't matter. So if we type that into our calculator right now, 44C6, we would get 7,059,052. So the probability, if we want to get fancy, we would say that's called our sample space. Probability of winning the top prize if the player buys 1 ticket. So if you buy 1 ticket, you're going to have 1 of these options. So the probability of the event occurring of winning would be 1 out of 7,059,052. And that's the answer. If you wanted to write that as a percent, I calculated that out to be 0.0000142%. But that's kind of ridiculous to look at it like that. The chances are really low, which is true for any lottery. All right, example 4, random selection. The number of colleges and universities in various regions of the United States during 2007 are shown below. 1 institution is selected at random. What is the probability that the institution is in one of the 3 southern regions? So first of all, we have to decide which regions are the southern regions, and it's going to be the 3 that say south in them. So we're going to have west, south, central, east, south, central, and South Atlantic. So that's going to be the 3 that meets the requirements. They're going to be in our numerator. A total of all of these numbers will be in the denominator. So we're going to have the probability of picking someone in the south, or an institution in the south, is going to be 738 plus 276 plus 406 over the total. And if you add all these numbers together, you're going to get 4,309, which is 1,420 over 4,309. That's a valid answer. You could also make it a decimal, 0.330, which would also be 33%. All right, so far, hopefully that makes sense. With probability, we have a numerator and a denominator. The denominator is the entire sample space, or all of the possible outcomes. The numerator is the ones that we're interested in that make our scenario a success, right? Whatever is given in the question. So let's look at example 5. In example 5, we are talking about a union of events. So let's back up here for a second and talk about what a union is. And we're going to be talking a little bit more about these definitions down here as we keep going. So the union, if A and B are events in the same sample space, the probability of A or B occurring is given by the probability of A union B. So union means A or B. It's the probability of A plus the probability of B minus the intersection of the probabilities between A and B. Let me show you why that is. I love that we have this nice Venn diagram here for this question. So let's just read the question and then we'll talk about the Venn diagram. One card is selected from a random deck of 52 playing cards. What is the probability that the card is either a heart or a face card? So we're going to say the probability of A is a heart and B is going to be our face card. So let me write down what that definition said from the front, and then we'll talk about why we do this. So it's a probability of A union B, which just looks like a U, and it equals the probability of A plus the probability of B minus the probability of A intersect B, which is an upside down U, kind of like an N for intersect. So we're going to write those next to that. But let's first look at this Venn diagram. So here are all of the hearts. in this circle. Here are all of the face cards in this circle, all the jacks, the queens, and the kings. And there's some overlap, right? So that's called the intersection, right? Which makes sense when you think about it like a Venn diagram. The intersection of the two circles would be the intersection, would be, you know, this what we do with this upside down U, this N. And there are 3 cards that happen to be hearts and face cards. When we say union or in probability, when we say the probability of A or B, that means that A might occur, B might occur, or A and B occur, right? Or means they could both be true in terms of math and probability. So we got to keep that in mind. So one or the other or both. So what we want to do is think about, okay, first of all, what's the probability of A? So what is the probability of picking a heart out of a deck of cards? Remember, there are 52 cards in a deck. And if we count all of these hearts over here, there are 13 hearts. What's the probability of picking a face card? If we count all of these over here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards. And then we have to think about what's the probability of A intersect B? How many overlap? And that would be these 3 right here, the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So that's 3 over 52. The reason we have to think about this is, let's say that we want to talk about all of the hearts. So let's say we include all the hearts. So I'm going to shade these in. And then we talk about that we're going to add all of the face cards. So I shade these in. If you look, we've included the Jack, the Queen, and the King twice. So we're going to subtract them once so that they're only accounted for once in our final answer. So we're going to have first all of those hearts, the 13 over 52. Then we add all the face cards, 12 over 52. And there's 3 cards that we've now included twice. So we have to subtract them once so that they're only included once. So 13 plus 12 minus 3 is 22 over 52, which is our answer, which we could say is about 0.423. And that's the probability that the card is either a heart or a face card or both. All right, next up, we're going to be looking at mutually exclusive events. If A and B from the same sample space have no outcomes in common, then they are mutually exclusive. So mutually exclusive would mean if we have a Venn diagram, they don't overlap. The 2 circles are separate. To find the probability that one or the other of 2 mutually exclusive events will occur, you can simply add their individual probabilities because they don't have any overlap, so we don't have to subtract anything. So that's the only difference with mutually exclusive events. They're exclusive, means they're completely separate. It's like if you exclude someone from your friend group. And mutually exclusive means like one excludes the other and the other excludes the first one. So they're mutually separate. So we don't have to worry about subtracting any overlap because there is no overlap. That's really all that's going on here with this one. So let's take a look at this question. The personnel department of a company has compiled data on the numbers of employees who have been with the company for various periods of time. The results are shown in the table. If an employee is chosen at random, what is the probability that the employee has A, 4 or fewer years of service, and B, 9 or fewer years of service? So let's take a look. For letter A, we're going to be saying that event A is 0 to 4 years, and event B is 5 to 9 years of service. So the probability of A is going to be 157 over the total. So if we add all these numbers together, we're going to get 529. And this is approximately 0.297. If these questions don't say show as a fraction, a decimal, or percent, you can choose whichever one you want. It doesn't matter. So either of these would be valid answers here. But there's a 29.7% chance that the employee has 4 or fewer years of service. For letter B, we're talking about 9 or fewer. So now we're talking about 0 to 9. So the probability of A union B, so A or B occurring, right? 0 to 4 or 5 to 9. In this case, it's going to be the probability of A plus the probability of B. Because these are mutually exclusive, we don't have to subtract any overlap. Those are mutually exclusive. So all we have to do is add them. So we have 157 over 529, which we already figured out. Probability of B from 5 to 9 is 89 over 529. So we add those together, we get 246 over 529, which is about 0.465. There we go. All right, example 7 is all about independent events. So independent events are two events. Sorry, let me restart. Two events are independent if the occurrence of one has no effect on the occurrence of the other. For example, rolling a total of 12 with two 6-sided dice has no effect on the outcome of future rolls of the dice. If A and B are independent events, the probability that both A and B will occur is probability of A times the probability of B. All right, so let's talk about the difference between that and mutually exclusive. So mutually exclusive events, that's when we're talking about one event occurring and there's possibilities that don't overlap within the sample space, but we're only talking about one actual event, right? In that example we were just talking about, we were talking about picking one employee at random. That was it. It wasn't pick an employee, then pick another employee. It was just pick one employee. In example 5, we were talking about selecting one card at random. Now we're talking about two events that occur, that are both going to occur, like rolling a die, then rolling another die, or rolling a die and then tossing a coin, or something like that. So when that happens, we're going to multiply probabilities together, similar to how we can multiply sample spaces together, or possibilities together, like the fundamental counting principle from a few lessons ago, where we would like multiply number of shirts times number of pants times number of shoes to get possibilities of outfits, something like that. Let's see what this means in example 7. A random number generator on a computer selects 3 integers. So you can already see we're selecting 3 different integers. It's not just one integer. We're selecting 3 different things. What is the probability that all 3 numbers are less than or equal to 5? Okay, so probability of this occurring once would be what? The integers from 1 to 5, that's 5 options, out of the integers from 1 to 20, that's 20 options. So there's 1/4 probability that this occurs once. So for it to occur 3 times, it's going to be the probability of A times the probability of A times the probability of A, right? Because all 3 times we're interested in the same thing, the number being less than or equal to 5. So it'll be 1/4 times 1/4 times 1/4. So 1 out of 64 times will this work and be true. Let's look at letter B. In 2009, approximately 13% of the adult population of the United States got most of their news from the internet. In a survey, 10 people were chosen at random from the adult population. What is the probability that all 10 got most of their news from the internet? So this is similar to letter A. We have this 13% number given to us, and we're talking about 10 different people. So it's going to be the probability of that one person getting their news from the internet to the 10th, right? It's as if we just multiplied by itself 10 times. So it'll be 0.13 to the 10th, which is going to be 0.1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. A really small number. That's another 0. So it's a point and then 8 zeros and a 1. So really low. That was in 2009. I would guess that number's probably a little bit higher today, but I don't know. All right, we've got one more vocab term to look at and one more example. So if we look back at the front one final time, we have this word complement. The complement of an event is the collection of all outcomes in the sample space that are not in A. Let A be an event, and let A prime be its complement. Sometimes we refer to this apostrophe as prime. So A prime is going to be the complement of A. if the probability of A is P of A, the probability of its complement would be written like this. And you could find it by doing 1 minus the P of A, right? Because it's like 100% minus the probability of A is going to be everything else that's left over, because 1 is everything. 1 is 100%. Let's look at example 8. A manufacturer has determined that the machine averages 1 faulty unit for every 1,000 that it produces. What is the probability that an order of 200 units will have 1 or more faulty units? So there's 2 different ways to approach this. First, I'm going to approach it by checking out the faulty units themselves. So to find the probability of 1 faulty unit occurring, what we'd have to do is that occurs once out of every 1,000 times. And so it's like the first unit that we examine would be faulty. And then we'd have to take into account that all of the other 199 units that we examine are not faulty, and they have a 999 out of 1,000 chance of not being faulty. Because remember, there's 200 units that we're examining. One of them has to be faulty. 199 of them have to not be faulty. So that would be, this would give us the probability of 1 faulty unit occurring. For 2 faulty units occurring, we'd have to do the same thing. The 1 over 1,000 would have to happen twice. The 999 over 1,000 would have to happen 198 times. And we'd have to keep going, because this question said, what's the probability that we have 1 or more faulty units? So we'd have to find all the probabilities for 1 faulty unit, 2 faulty units, 3 faulty units, all the way to 200 faulty units, and then add all those probabilities together. And that's going to be kind of crazy. So I'm going to write that out so that you can see in words what I'm saying here. So we would need to find all of these probabilities and add them together. Or we find the probability of no faulty units So let's do that. Probability of no faulty units would be 999 over 1,000 to the 200th, which is about 0.819. If you use your calculator, because it's 999 over 1,000 is the probability that any given unit is not faulty, and we're examining 200 of them, so we have to multiply by itself 200 times. So there's 81.9% chance that all of those happen to happen. So we can find the probability of no faulty units, and then find the complement. Remember, that's A prime. So the probability of A prime is 1 minus the probability of A, which in this case is going to be 1 minus 0.819. So we get 0.181 as our final answer, which was much simpler than finding 200 of these calculations and then adding them all together, right? Because, you know, the options out of 100%, there's going to be a certain percent that have no faulty units, and there's a certain percent that have any number of faulty units, right? Those are the only two options. So if we do 100% minus that, we'll get our answer. Hopefully that makes sense. And that's the end of the notes. There's a basic introduction to probability. Hopefully that makes sense. Please let me know if you have any questions, and have a great day.